Okay. Next presentation, Xiong from Harbin Engineering University. He will present, please share your screen.
Okay.
Yeah, please share your screen, Xiong.
Yeah, can you see the screen?
Yeah, but presentation we can see. Yeah, I can see. Okay.
Yeah. Okay. Okay. I'll start.
Okay, it's okay. Just wait
Yeah. Okay. Okay. Okay.
Yeah.
I'll
Now it's
start.
okay.
Okay. Okay. Hello, everyone. I'm Xiong, a PhD candidate.
We
Mhm.
can wait 2 minutes.
1 minute.
1 minute. Please wait 1 minute.
Mhm. Okay.
Yes, yeah, only presentation. That's right. It's okay.
You can start, please.
Okay. 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 Thank you. Hello, everyone. I'm Han
We
Xiong, a
cannot see
PhD
your
candidate.
screen. Okay.
Mhm. Okay.
All right. All right.
From what?
All right. Please go ahead.
Yeah. I'll start. It's a pleasure to make a presentation here. The length of it is the vertical motion of a circular cylinder in water covered by an ice sheet. My presentation includes 4 parts. The first part is the background of this work. As global warming and the melting of sea ice make valuable resources in polar regions, there has been a recent increase in exploration and utilization of underwater areas in polar ice regions by underwater vehicles. One of the main challenges for underwater vessels operating in the polar ice regions is to brake safely through the ice in emergency situations. Besides some new ice braking methods, including ice braking by high-pressure air gun bubble, ice braking by high-speed water jet, it is known that the ice cover can be weakened and even broken by fractal gravity waves generated by a body moving above or under the ice cover. The deformation and even destruction of the ice cover caused by the movement of the underwater objects have been shown in many theoretical and experimental studies. In theoretical studies, point sources are often used to model objects moving horizontally under the ice cover. A slender body moving at constant speed in a bounded liquid can be modeled by a source sink system. Moving circular cylinder and sphere in a bounded liquid can be modeled by a 2-dimensional and 3-dimensional dipole of a certain strength correspondingly. From the present studies, we may conclude that the main part of research on ice cover deflection caused by a moving under the ice body was done for horizontal motions of the body at a constant speed. From this review, at present we investigate the problem of a circular cylinder moving vertically towards a floating ice cover from below. The cylinder with radius A is rigid, and the ice cover is modeled as a thin elastic pump with uniform thickness. The motion of the underwater cylinder, the liquid flow crossed by the moving cylinder, and the response of the ice cover are coupled and should be determined at the same time. The second part is the formulation of this problem. The upper boundary of this problem is governed by thin elastic Planck equation, which can be decomposed. The hydrodynamic pressure in the flow region shown in figure is given by the nonlinear ballooning equation. The position of the cylinder is described with the Cartesian coordinate and the polar coordinate system. The velocity potential satisfies the Laplace equation in the flow region and the far field condition. The moving cylinder with outward normal gives the surface boundary conditions satisfied by the velocity potential. And the effect of the small ice deflection on the floor and the hydrodynamic pressure comes through the elastic ice-liquid interface condition, which is linearized, and we do not account for the shape of the ice-liquid interface, but only for its velocity, which should be small compared to the velocity of the body motion. The hydrodynamic part of the formulated program is transformed by using the conformal mapping method, which maps the original flow region to a ring. There exists a potential function in the conformal mapping ring corresponding to the velocity potential in the original flow region. The original boundary value problem can be transformed to the similar problem with that potential function with r theta. The boundary value problem have a solvable condition which further gives the deflection W satisfies such a condition. Based on these conditions, the deflection can be written in a Fourier form. We based on the Lorenz series from the deflection and the relationship between x, y, and r theta when y equals to 0. Take the first derivative of w with respect to t. We obtained the expression of partial development of w to t. Similarly, we can take the derivative of w with respect to x. Then we obtained the expression of derivative of w to x. Okay, then we substitute the partial derivative of w with respect to t to the boundary value problem of the potential function within the conformal mapping ring. The velocity potential in the fluid field can be solved by separating of variables method. The velocity potential is related to the deflection coefficient of the upper surface boundary. And then these coefficients are known metrics related to n. And then substitute the known expressions of velocity potential like including the Wt and phi and velocity potential u in the upper surface, and then innovating the term of 1 minus cosine n theta. Finally, an infinite system of ordinate differential equations in the form of vector about w and u is obtained. And similarly, substitute the known expressions in ut and w in the upper surface, innovating the term of 1 minus cosine theta. An infinite system of ordinate differential equations is also can be obtained. It's the form of vector about w and u. Finally, the upper surface condition will provide an infinite system of differential equations, which needs to be numerically solved. In the present study, the fourth order Runge-Kutta method is applied to solve it with the initial conditions. The third part is about the numerical results. Firstly, the convergence analysis is carried out with respect to a finite term n, which truncated the ordinary differential equations. It can be seen from the figure that there is a little difference between the results obtained by n equals to 40 and n equals to 50. The measurements to the negative 6th power of 10 and as for the strain, it is about 9 to the power of 10, indicating that the convergence of this problem has been achieved. And then is the validation. Firstly, is a hydrostatic model is provided here, and it is only the elastic plant with a given time-dependent node and also including the hydrostatic force. This problem is solved by the approach mentioned before and the Fourier transform method at the same time, and then the results calculated by the two methods are compared here. The comparison of the deflections calculated by the present method and the Fourier transformed method are compared. Here is the 3 time instance is selected here with the time stable. Note the spatial form of UT is selected here. And then the coupled hydrodynamic model is provided here to add including the fluid effect. It considers the liquid and the hydrodynamic pressure based on the hydrostatic model. And also, it is solved by the approach mentioned before and the Fourier transformed method at the same time. And the comparison of deflection calculated by the present method and by the Fourier transformed at the same time instance are calculated and compared. From the it can be seen from the figures. The results are in good agreement, and the next, the results are provided in figures. This is the linear case of the formulated problem. The nonlinear term of the hydrodynamic pressure is ignored here, and it is solved by the approach mentioned before. It is provided here to compare with that of coupled hydrodynamic pressure, hydrodynamic model when the cylinder is far from the ice and the external lower node is small. The comparison of the long-dimensional deflection and the velocity potential is compared here, and the figures shown that they are in good agreement, which indicating that the response of the elastic plant with this model and the coupled hydrodynamic model are the same when R tends to 0. It means the cylinder is far from the ice cover, and the external lower node is small enough. From these 3 validation cases, we can indicating the results we calculated are the right. And then for the maximal deflections here, we provided the cylinders moves at constant speed with the unchanged initial depth. As for the cylinder moves vertically at a constant speed, the plant deflection above the cylinder center increases when it gets close to the plant. This shows that the deflection value is affected by the distance between the cylinder and the plant. Delta is the changing emergency depth of the cylinder, which corresponds to the distance between the cylinder and the plant. We can see in the figure, when the speed of motion increases, the maximum deflection crossed by the cylinder, reaching at the same distance, will increase. And there is a spatial value of moving speed. When bigger than it, the maximum deflection corresponding to a certain distance of the cylinder and the plant during the motion will not change. For example, for the delta equals to 0.2, when the velocity is equals to 40.7, the maximum deflection will not change. Also, it is similar here for the maximum strain. There's also a spatial value of moving speed. It's bigger than it, the maximum strain corresponding to the certain distance of the cylinder and plant during the motion will not change. Also, we can see from this finger and this finger, we can draw a conclusion that the effect of the nonlinear term in the hydrodynamic pressure affects the strains more. And the fourth part is about the conclusions. When the underwater cylinder moves at a constant speed from an unchanged initial depth, there's a spatial value of moving speed. It's bigger than it, the maximum deflection and strain corresponding to a certain distance of the cylinder and plant during the motion will not change. The spatial value of speed corresponding to different distance between the cylinder and the plant depends on the distance. It increases when the distance decreases. In addition, the nonlinear term of hydrodynamic pressure distributed along the interface affects the maximum deflection and strain, and also the spatial value of speed of the formulated problem. And also, the more numerical results remain to be calculated and draw to conclusions. Thank you for listening and guiding.
Thank you very much for your nice presentation. Now we can ask
Yeah,
questions.
thank you.
Any question from the auditorium? Okay, then I have a few questions.
I have a question.
Please.
Hello.
Yeah, hello.
Yeah.
Yeah, when you talk about the convergence analysis, can you explain that? How you decide if this convergence or not?
And it's for the convergence analysis.
Yeah, the convergence analysis.
Mm-hmm.
Yeah, you said it's convergence, but how?
It's the several term. The several term is infinite, then we should transject the severals with the finite term, and then we increase it and compare the results calculated by different n, and then compare and then we compare the results, and the difference between them are shown in the figures. It is small enough, so we draw a conclusion that the confusions is enough.
Okay, thank you.
There is a question from Mike Milan. Is this approach can be extended for three-dimensional problem?
Sorry, I didn't listen clearly.
Is your approach can be extended for three-dimensional problem?
No, at present we consider the two-dimensional.
Yes. I have a question. The cylinder start motion. It is a impulsive start or slowly start from zero velocity or from some finite velocity.
Yeah, yes. In this presentation, we consider it moves at the with the initial v. It's not zero. It's just starts suddenly with a certain v. It's with a certain speed.
So this is impulsive start. Yes, it's called impulsive.
Yeah. Yes.
And about the method of solution, you use conformal mapping flow region to the annulus, and how you I believe you already presented formulation of the problem in the annulus. Can you show the so the in radii correspond to the boundary of the cylinder?
Oh, Yes, the upper surface with y equals to 0, it corresponds to r equals to 1. And for the surface of the cylinder, it corresponds to r equals to capital R.
So how to solve it? So you have boundary condition on the annulus, on the two radius. How solve it, this boundary value problem in annulus? What is solution of boundary value problem formulated in the annulus plane?
You mean this one? It's there's the velocity potential in the original flow region, and it's corresponding to a potential function in the ring region.
Okay, thank you.
We have enough time for this.
So we have enough time. Please ask questions.
Hank, can you please go to your convergence result?
Okay. You mean which slide?
Your convergence results. You have not put any slide number.
This one?
Go down, no, where the convergence is studied. Go to 18, probably. Yes, here, 17. How do you means find that convergence result? Here only one picture we can see for red line for n equals to 50. Where is the line for n equals to 40?
What? 40? Sorry.
Yeah, we can see only, no, earlier slide, 17. In slide 17.
One?
Yeah.
Yes, this one.
If you check the results, we can see only red curve, red color curve. Where is the black curve? We can see only one result.
Yeah. Oh, I'm sorry. You may there's a misunderstanding here. It's just one result, but the is for the results W n equals to 50 minus minus the W n equals to 40. Yeah, it's only the one result here. It's 19. Yeah.
Okay. What is mu in your formulation? Mu. What does it represent? Mu. You can see on top Wn4 by mu to the power 4. What is that mu? You go to the formulation. Mu.
Do you mean the view, the potentiometer view?
Yeah. Yes, that mu. What is that represent?
Okay. Mu equals mu. Okay. Let me see this one. It is here. H equals to H refers to the distance, the immersion depth, and A refers to the radius. Mu is here. We provided here. Yeah.
Okay, HT minus. Okay. Okay, thank you from my side. You can ask any other questions.
Thank you. Any other question, please?
Or we can have it.
Otherwise, so we have 8 minutes for the next, before next. Take a break.
Thank you. Yes, stopping. Say thank you.
Thank you very much, Xiong.